Okay,
Yeah.
Prof. Good morning.
Good morning. How are you?
Good morning. Good morning, house.
Yeah.
It's been a while again, Prof.
Yeah. You're
It's a
welcome.
pleasure to always have you because in every engagement
Yeah.
we are always full of new experience and full expectations. So, Prof,
Yeah.
I really appreciate how far you have gone with us, and
Thank
may God continue to prosper you.
you. Amen.
So, Prof, yes, just a little clarification
Okay.
to few of our colleagues who are on the platform. There's a project we are involved by grace of God through your mentorship and so on. The methodology we are adopting our process has actually aided the project to escape to get to the stage we are. May
Mm.
Almighty Allah reward you abundantly, sir.
Amen. Thank you. Amen.
Yeah, most of the senior colleagues who are in the team from my institutions and the collaboration are right here in the platform. And they just need a little clarifications because we'll be going for a defense, which is very crucial. And I pray that you will rejoice with us. We adopted, we are adopting an assemble, a stacking assemble
Method. Yeah.
machine learning model
Yeah.
algorithms.
Yeah.
Yes, sir, method. Please, uh, I want you to just shed light in this aspect, particularly to people who are, they are distinguished. They have been in the academy, but they have been over time used to the conventional analytical method. This method is new to them, but we thank God it has scaled us through. They need a little clarification. They need what they can put on the table to allow this our project to scale through, sir.
Okay.
That is just all I want from it. Clarification.
Okay. Yeah. So
Yes, sir.
thank you very much, Salami. Thank you very much. And I hope you are making very good progress in your PhD work. Wishing you all the best. It has been a very consistent attendee at this particular weekly program for several years now. Maybe since we started, he has been very consistent, and I want to believe he has done a lot of work in this respect. And wishing you really all the best. As you also encourage others. Like I said, even if you are new, you are all welcome. You can still meet up. Now, to his question, yeah, one of the when things get really tough, see, when things get really tough, you can see here, yeah, you can see here when I show you this the other time. Yeah, remember I show you this extensive, yeah. You see, once we start the modeling, see, you bring in your data, always work with the principle, let the data speak. We'll come back to Mr. Dr. Idris Sani, who has raised his hand, but we'll come back later. Just hold on. Thank you. So once you have it, don't forget the multi-channel approach. It's very important. You have to run many multi-channel, channel 1, channel 2, multi-channel pipeline. So run your data fresh, do the necessary stuff I mentioned, do the hyperparameter, do the tuning of the optimization, changing the algorithm to the chain tree, support vector machine. Sometimes you may even need deep learning, but you don't need deep learning for everything. But if it involves videos, text, and images, then deep learning is your first point of call, especially to do automatic extraction of the features. Because that's the strongest point of deep learning. It can extract feature for you without human intervention, especially when you need real-life, real-time application. Once you extract the feature using deep learning, you compare it with other standard machine learning algorithms. We have tested it. Sometimes ordinary k-nearest neighbor may perform better than deep learning in some problems. This is another thing people don't understand. You see? But if your data sets is their number, little label systems, go for standard machine learning algorithm. Don't use, when you use deep learning for a very simple algorithm, it's like using a sledgehammer to kill a fly. The fly may escape from your table, but you may end up breaking your table. That's the analogy. So when you select algorithm based on the complexity and what you are looking for. So once you have this turning of changing the algorithms, don't go here to ensemble. Try other pre-processing. Go back to this, maybe your features, because what you need to get better result may be lesser. Ensemble will give you, of course, the advantage of ensemble is it guarantees that you always get better result than individual algorithms. So when you go to ensemble, which is the point of question that have been asked, there are different types of ensemble, and I also want to recommend to us in the team of that project, let us watch. There is a series on ensemble machine learning modeling on our YouTube channel. Dr. Salami, you can check that one out, or you can contact. We'll provide you with the link to that playlist. We have several videos on ensemble. We describe all the type of ensemble, starting from the classical boosting, bagging, and the newest method with the one we call stacking. Stacking avoided the problem of boosting. In short, in bagging ensemble, we don't consider the performance of each algorithm. Everybody has one vote. The vote across board. So you train algorithms and let them decide what is the answer. A, B. Majority carry the vote. If 10 model says this is correct and 9 said it is not correct, we go for it is correct, even though it may not be the correct answer. Because if you have medical doctors that are senior professors, even they are only 2, their decision may be better than 7 training doctors in terms of decision making. But bagging does not take care of that. In boosting, we give more importance to more qualified, more accurate algorithm or model after the training. The problem with that is we multiply. We have a professor of medicine with 25 years of experience, another junior doctor, 5 of them say don't go for surgery. Those 2 professors, because we respect them much, we multiply their decision by 3. So 3 times 2 professors, that will be 6 years. Go for surgery. Those young doctors, they said no. 5, that is 6 against 5. Even though 5 doctors recommended don't go for surgery, we will go for that surgery because 2 professors that are highly respected and we gave more weight to their voting said go for it. But don't forget, professors are also human beings. They may make mistake. So when they make mistake, we'll be multiplying their mistake by 3. That's the problem of boosting, in summary. So this is why stacking now came as a way of solving the problem of bagging and problem of boosting. What is stacking? Stacking is saying that when you use this kind of system, you are going to train an algorithm. You train like multiple classifier, KNN, decision tree, support vector machine. Train many of them. The more, the better. In one application, when Netflix put up $1 million for whosoever can improve their recommendation system by 10%, just 10%, they put on $1 million on that project. A lot of people try. No one can win that particular award, except they came together, team from different countries. They brought the algorithm together, their models, and they were able to combine them together. Able to build the system they had. Okay. So what I was saying there is that the more the number of models you build, the better. Sometimes they build like 155 models and then they combine them. So they take a decision. Stacking, instead of voting, either boosting or bagging, stacking does not do voting. It goes ahead to train another model again. There's a final model, ABS-VM. You can try different algorithm here also. So Instead of taking yes or no from them, it doesn't take yes or no. From K nearest neighbor, it takes in, okay, when you say yes, you need something to say yes. The yes came from maybe naive Bayes, for example. It came from the probability. Probability of yes is 0.8. Probability of no is 0.2. So in stacking, you bring in this 0.8 and 0.2 as a feature. You take it like it's feature. You don't just take yes. We know this is yes now. We don't need yes. We need 0.8, 0.2. This is another variable now. We take that as new feature. This one also comes with its own, maybe 0.7, comma, is 0.3. Support vector machine its own as maybe 0.2. It doesn't believe that it should be yes. It believes that it should be no, 0.8. We get all these features will now be used as input to support vector machine, to train support vector machine to generate the final yes or no. So it performed wonderfully well on several applications. So if anyone's making a proposal, I strongly recommend to go for stacking because it avoided the problem of boosting and also bagging while ensuring that you are able to get something better. However, I always, with the principle of let the data speak, so I always recommend that we are very careful. When you are writing, for example, when you are writing a proposal, people used to say you must mention the algorithm you want to use. I used to tell my colleagues, please, let us be flexible with these students. When they get to the real implementation, the algorithm he has mentioned may not work. So permit him to mention, we are going to use social algorithm this while also considering possibility of exploring others. You have to always put it in your proposal. Because the principle of let the data speak means sometimes what you think will work for your data may not work when the real data really arrive. So machine learning encourages us to try different options. Try bagging, boosting, and stacking. But in majority of cases, stacking has always performed better than others. But then we may not be able to tell, depending on the kind of data you are bringing on board. So always let the data speak. I hope that gives some clarification to the team members present, while also recommending for them to watch out, to go and check out our YouTube channel for those videos. Dr. Salami can work in this respect to provide your team. And if you need further consultation on this, feel free to also reach out. Thank you very much. I think Dr. Sonny or Mr. Sonny, someone raise up hand. Idris Sonny, you have the floor. You can ask your question. We have 3 minutes more. Okay. Unmute yourself. You need to unmute yourself. Yes, you need to unmute yourself and talk. Are you still there? Idris Sonny? Okay. Yeah. Okay. Go ahead. Oh, we can't hear you. Is it from my side alone? Hello? Yeah, I said you can go ahead. You say you raise your hand. Do you have a question? Can you move closer to your mic? You are far away from your mic. Please get closer. Yeah. It's better now. Please move closer to it. Yeah, it's getting better. No, we can't hear. I can't hear you.
Can you hear me now?
Yeah, we are hearing you now. You said raise up your hand, please, your voice, please. Yeah, it's better now.
Good morning, bro.
Good morning. How are you, sir?
Thank you for the very clinical explanation.
Sorry, you have to maintain that closeness, please, and voice loud. Your voice went down. Yeah.
Hello?
Hello, yes.
Can you hear me now?
Yeah, we can hear you, but not very much. Yeah.
In class for
Yeah,
me
yeah.
this morning. This is my first time of appearing on this platform,
Okay.
and I think I have learned very, very deeply this morning. I really want to thank and appreciate what you have done. So my question is very simple. For us that are beginners in this class, on this class, uh, for somebody to use machine learning as a methodology of analysis for analysis in a project, precisely, they say there are 3 steps. I want you to explain the 3 steps involved for me, seriously. Thank you, sir.
Okay. What do they mean by there are 3 steps? There are many steps we take when we build. So it depends from which angle the person is mentioning. So what are the 3 steps they are referring to? We have several steps we take when we building.
What I mean is this.
Yeah.
They say, one, there is the learner stage of data collection. After that, you go to meta stage before the hybrid algorithm. Is this thing that is very confusing? At what stage do we now use for policy implementation or proposing for policy implementation?
Okay. Okay. Thank you. I got your point. Thank you very much for that. Again, if you look at here, look at this I showed you before. You are highly welcome, Dr. Idris, to the class. Yeah, I've been the first time of you are highly welcome. And like I said, you are not late, so you can always meet up. But just be ready to learn some things personally. I mean, watch those videos. I want to believe the links to those videos will have been posted now in the platform. So join our WhatsApp groups so that regularly we do make announcements and guidelines. And we also have research groups where people are working together collaboratively. A lot of the groups have published paper together as teams. So together, making us to be productive and taking advantage of this unique technology. Now, to your question, yeah, usually you have, that was why I asked that when you talk of 3 steps, there are many steps we take, but in this respect, let's say this is your data. Once you get the data, once you get this data, I said, do minimal preprocessing. Don't do too much preprocessing because some of them may not be needed so that you don't mutilate your data. You go back as the need arises. If the original data is not able to speak clearly, then we go back and do some things. PCA, principal component analysis, seizure feature selection, clustering, so many things we can do. However, once you have your data, this is where the actual machine learning modeling takes place. And it has that was what I was thinking you want to refer to. There are 2 steps here. Some people make it 3. And what are they? The number 1 is training. Training. We train our model. We divide our data into 2 or into 3. If you have huge number of data, you divide into 3. We have training sets. Then we have 2 testing sets. And then 3, we have the validation set. Some people can put validation at 2 and put testing to 3. Doesn't matter. Testing, validation, we are doing the same thing there. So as the case may be. So that's why I said, from which angle are you looking at the 3 steps? In this step alone, we have another 3 sub-steps here, where you divide your data into 2. We use 70% of the data for training, and then use 50% for validation, and another 50% for testing, making 100%. See, that's when you are using the partitioning method, hold-out method. We call it hold-out method. You use some data to train and hold the other one out. We also have another type we call the cross-validation method, where you don't want to divide into 2 or 3. We use all the data, but we divide them into 10 portions or 5 portions. You use 9 portions for training and 1 portion for testing. Every portion will be used for testing 1 time. Use 1 to 8 portion plus 10 portion for training and the 9th portion for testing. You keep doing that until you use 2 to 10 portion for testing and the first one for training and the first portion for testing. So every portion must participate in testing. This is the one we call cross-validation. We use it to test proof of concept. And we use it most importantly when your data is very few. Sometimes you have data like 15 samples, 20 samples, 45 samples. They are very few. If you divide them into 2, how many samples are you going to have? That's why we go for cross-validation in that respect. But when you have enough data, then you go for the partitioning method, training, testing, and validation. But divided to 2 is okay. What do? Divide to 70% for training and 30% for testing. That is fine. You don't do a validation. But this 70%, you must make sure you don't use this 30% during the model building. You keep this outside your modeling. So in the model building, you can use cross-validation on the 70% to do your training and testing. To do your training and validation. Later, you bring this testing result from outside to come and check if the result is okay. That is one area of doing it. Sometimes this 70%, you can divide it into 2 again. You see, 70% divided into 2, training and testing. This 30, you didn't touch it. They are outside. Once you finalize with your model, you bring it later to check that it's fine. Once I've checked with this, then I can then deploy. Maybe the data was brought by a company to me. I didn't talk to the company. Now, thank God, we got a very good result with your data set. We need to move on now. This is where I've checked the performance measure. If it's doing fine, then we can now go to the result analysis and discussion. You now analyze and discuss your results. I have another flow chart for this, but it's not in this slide. So, but however, when you go to those videos I recommended, those 4 videos, I want us to watch it. As a newcomer, it's compulsory. You get to understand machine learning in a simple way. There are ways people present machine learning. It's very tough time. They start talking of Python. I don't know why. You don't need Python to be able to use machine learning. You see, there's difference between programming languages and AI. So without writing a single code, you can use it for your own project analysis. So, but you need to understand how it really works. So this is just one aspect. Training, testing, and validation is just one aspect of it. Once you are done with your data collection, feature engineering, you move here, you do it, then you go to performance measure, you check. Once the performance measure is okay, good. You can then go to what we refer to as result analysis. And policy, whatever, formulation and implementation. For example, under this analysis, this is where the real discussion takes place when you want to write report of your modeling. Let's say somebody is predicting if somebody is sick of diabetes or not. He got like 98% in the result. However, there are 2% mistake. Now, you know there are 2% mistake. But the 2% mistake, they are false negative. False negative means people who are sick of diabetes, but that AI is saying they are not sick. So they will go home and they have complication. And somebody built his own model, he achieved 97% accuracy. You know, AI, there's 3% mistake. For all the mistake, they are false positive. False positive. Let's pay attention. This is what we do in the analysis and discussion of results. When I'm going to select the final model, I will go for 97%. This is the one we are going to deploy for the client. Why? Because the cost of the mistake of 98% is higher. When somebody is sick and you say he's not sick, he will go home thinking that it's fine. He will develop complication. He may lose his life, and the company may be held responsible. Because when AI make mistake, the one using it is the one that is held responsible. The hospital that deployed that AI will be held accountable for it. But for this 3%, the mistake is a good mistake. We don't want any mistake, but in life, there will always be mistake. False positive means he predicted that some guys are sick of diabetes, but when the guy went to the clinic for checking and the lies, they found out that it was a mistake. Those guys were not sick. They were perfectly okay. So this kind of mistake we call it, it has lesser implication. Those mistakes, they have lesser implication. So we can relate with it. So this is what we do. After you have checked your performance, you have improved it, and you are satisfied with what you have gotten, then you move to result analysis and discussion. This is where you are going to discuss the implication of what you have gotten, then the policy formulation you are going to recommend, and host of other reality that needed to be put in place. Once again, I welcome you on board, and then I recommend watch those videos so that you can get the introduction. Note down whatever is not clear to you by the grace of Almighty God. By next week, you can also come around and then ask whatever question that you now find okay. Some of these questions you ask will have been answered in those 7 videos. Inshallah, God willing, so that you can come back and then be able to clarify further as the case may be.
Thank you, my bro.
Thank you for coming. Dr. Idrisani, is that okay?
Thank you so much. I really appreciate.
You are welcome. You are welcome. And last but not the least today, Olanyinka Bukola, we'll take your question, although we'll be out of time before we call it a day. Olanyinka Bukola. So
good morning, Prof.
Good morning. You're welcome.
Thank you very much, Prof. Today
Yeah.
is my first day, okay?
Okay, you're
But
welcome.
I was very, very impressed, sir.
Yeah.
Thank you very much, sir.
You're welcome.
My own is I don't know if you will give me an opportunity to just say 1 or 2 on the first thing. I'm a PhD student.
Okay. You're welcome.
Of Federal University of Engineering. Yes, sir.
You're welcome.
So just I was caught up with the first person's question.
Okay.
On is assembling and hybridization.
Okay.
So at this point, I think he should try to also understand the fact that what problem is he trying to solve? Because some problem might not entail assembling. Some problem might be hybridization, and you are thinking assembly will solve the problem. When using assembling, the main aim is to improve accuracy. Meaning, maybe you are combining 2 algorithms together, but the result of one becomes the input of another. Probably I'm using KNN and SVM, for example, support vector machine. Now, the result of my KNN will now be the input to my SVM, that is assembling. Maybe there's an existing work that I want to improve on the accuracy, because at the end of the day, there will be performance evaluation. But why using hybridization? Because I was just carried away with his question. Why using hybridization? You are bringing 2 technologies or combining the model together, whereby both of them combine to give one result. So I think just to shed more light on when to use assemble and hybridization, that is just the little.
Okay, thank you very much.
I've been using it.
Thank you, Olanyinka Bukola. That's a very good one.
Thank you.
Happy to have also people like that on the forum. I really appreciate. However, let me shed further light from the angle you have spoken. Okay. Yeah. Hybrid and ensemble. The ensemble principle is that you let 2 or more, the more the better, model, let them collaborate to take a decision. Let them collaborate to predict. This one is predicting, I want to predict the age of students in my class. And it has been established that ensemble modeling performs better than individual model, irrespective of where they come from. Real life example I've indicated. We have them to make a guess of the age of somebody, and we have a group of people to make the guess, and we find the average of their guess. The average of the guess is always closer to the original age. It has been demonstrated. We have balloons in a room. They put balloons, several balloons, on which student, like 100 students, wrote their name on that balloon, the same color, and they threw it down into a room. They separated them randomly. They asked them to go and pick the balloon. It took them several minutes before because some students may pick balloon up to 99 balloons before they pick their own. Pick this, it's not mine. Throw it down. Pick this, not mine. But when they use ensemble collaboration, they said you just go there, pick a balloon, read the name, and give it to the owner of the balloon. Within few minutes, all of them got their balloon. That is the power of collaboration. That is what ensemble entails. And that is why most of the competitions, like the Netflix $1 million stuff, they always got the winner always using ensemble. That is the unique power of those ensemble when we collaborate. And the unique thing is this. You see, every algorithm, we favor using different algorithm than just modifying a single algorithm. When you modify the same algorithm to generate different model, we call them homogeneous ensemble. Homogeneous ensemble. So I have maybe neural network with 10 layers, another one with 15 layers, another with 20 layers. They are all neural network, but with different topology. They will generate different model. This is homogeneous. We encourage heterogeneous ensemble. You can build like SVM, maybe 3 from SVM, decision tree, k-nearest neighbor, logistic regression, and also further ensembles. When you have mixture of this, the reason why when you mix different models, they perform better is each model, each algorithm has different hypothesis space. They have different hypothesis space. The hypothesis space for neural network is different from the hypothesis space from SVM. They operate at different level of hypothesis. Therefore, this guy will be looking at the data from another angle. This one will look at it from another totally different angle. So when you put heterogeneous ensemble together, it's very, very tough and challenging to really see other algorithms that perform better than them. However, the hybrid, like the stacking he mentioned, stacking is considered hybrid model also. That is why it is unique. Stacking is not just doing stacking is not doing voting. It's doing exactly the explanation of hybrid you said. The first hybrid we built was when I remember then when I was doing my PhD, we built a hybrid model using type 2 fuzzy logic. Type 2 fuzzy logic will be able to resolve some of the uncertainty in the data set. After it has resolved the uncertainty and do some unique cleaning, we pass it to extreme learning machine, who will do the final prediction. This is a classical hybrid model. You start with an algorithm, the result is passed to another one for training and testing. In stacking, that is why it is so unique. It's like an hybrid ensemble model, 2 concepts combined. Because the stacking, we start with many models, like we have here. They've come, it will not vote. Rather, the output of them, like I gave before, the probability of yes, 0.8, and probability of no will be collected and be used as a new feature to train another model. That model may be support vector machine, it may be k-nearest neighbor. So it means the output of these many models are being sent as input to another model. That is a classical hybrid model, but the fact that they are also ensembling, that's why they call it, it's more of an hybrid ensemble. So some of the latest technology of ensemble, they are trying to combine both the idea of hybrid and also ensemble concept together. So that is why stacking, even though considered an ensemble model, it is more or less also implementing an hybrid modeling indirectly. So, and like the principle of let the data speak, I agree with your position. You cannot be sure what is going to work for you. You know, I mentioned that. I said, don't use sledgehammer to kill a fly on your table. You may end up missing the fly and breaking your table. So start from simple algorithm. This is the principle of machine learning. I've mentioned it here, and I'll refer us to it again. So for clarity, see, here you have, see, start with raw data before applying too much preprocessing. Always use the iterative process. Remember, machine learning is not a dogma. Try different algorithms. So we cannot assume from the beginning that this is the algorithm that will work for us. That is wrong. The let the data speak principle says, you can start from the simple. In fact, the recommended principle is to start from simple algorithm and move gradually to more complex algorithm. So you don't just pick a problem and go to deep learning. And I've seen practical mistake people made. There was a paper published, they achieved 85% accuracy using deep learning for safety in the oil and gas company. When I look at the data, it was data set numbers. I said, why using deep learning for this problem? I immediately put the data in k-nearest neighbor, one of the simplest algorithms. K-nearest neighbor was getting 95%. Without much work, look at it, 10% improvement with simple algorithm. They used deep learning and they got 85. And it was published in a Q2 journal. So a lot of people are missing that, the idea of making it simple and only go to complex when it becomes necessary. Thank you very much all for listening. I believe that is more than enough for us for today. Thank you very much. And until next week, we're wishing you all the best. Thank you very much.